An insulator with a hole. Part A. An insulating sphere with radius A has a uniform charge density ρ. The sphere is not centered at the origin, but at r is equal to b. Show that the electric field inside the sphere is given by E is equal to ρ r vector minus b vector divided by 3 epsilon 0. So we note that we have a uniform surface, a uniform charge density, volume charge density ρ. For a sphere, the sphere is centered at r is equal to b. Okay, so let's look at the sphere. So here are the x, y, and z axes. Z is coming out. So you have z coming out. This is centered at r is equal to b. So r is this vector that is drawn from the origin to any point in space. And this is centered at r is equal to b on the x-axis, let's say. And the sphere has radius a. It has a uniform charge density ρ. And if we take a Gaussian sphere inside this sphere with radius r prime, we can calculate the electric field at r is equal to r prime, which will be less than the radius a. So for the total charge enclosed by this sphere, we can say that Q, the total charge, will be equal to the charge density ρ multiplied by the volume of the sphere 4/3 pi a cube. Why? Because we have a uniform surface charge, a uniform volume charge. Now we can write Gauss law. Gauss law states the closed surface integral E dot dA, the net electric flux, is equal to, now we have radius r prime here for this Gaussian surface. The electric field lines will be pointing radially outward in this direction, and they will be only dependent on the value of r prime. So we have electric field magnitude the same at all points, and the area vector is pointing radially outward. So we have E dot A giving us E times A, because we have zero angle between the area vector and the electric field, and the electric field magnitude is a constant here at r prime. So it's going to be E times the area, which is 4 pi r prime square. This must be equal to the charge enclosed by this Gaussian surface, Q in, divided by the permittivity of free space, epsilon 0. So we can see that the electric field magnitude times 4 pi r prime square must be equal to the charge enclosed, which is the charge uniform volume charge density ρ multiplied by the volume. What is the volume of the sphere? 4/3 pi r prime cube, and that's going to be divided by epsilon 0 according to Gauss law. So you can see that we're going to have a cancellation of r primes here. So 4 pi r prime square from the left side will be getting rid of this 4 prime, and this r prime cube will become r prime. So what am I left with here? Rho r prime divided by 3 epsilon 0. So I conclude that the electric field vector will be rho r prime divided by 3 epsilon 0 in r prime hat direction. It will be pointing radially outward in r prime hat direction. Now, what is the relationship between this b vector, which is the vector drawn from the origin to the center of the sphere, the r vector, the radial position vector, and r prime vector that is drawn from the center of the sphere to any point in space. Now you can see that the relationship is r prime vector is equal to r vector minus b vector, right? So you can note here that b vector is b in I hat direction, r vector is r in r hat direction, and r prime vector is r prime in r prime hat direction. Now, this is going to be equal to then r prime in r prime hat direction. So I'm going to replace r prime hat with r minus b. So I will see that the electric field is rho, the uniform volume charge density rho, r minus b divided by 3 epsilon 0, which is the permittivity of free space. All right, so that's basically what we were supposed to find in part A, the electric field inside the sphere. So this is going to be valid for r prime less than a. So that's the, because r prime is basically related to this vector r vector minus b vector. We have this relationship, and r prime magnitude, which is the magnitude of r minus b vector in the direction, in the unit vector direction, in the direction of r prime hat, it should be less than a. So that's basically taking a radius less than the radius of the sphere a. So that's the condition we have in mind. Now in part B, an insulating sphere of radius capital R has a spherical hole of radius a located within its volume and centered a distance b from the center of the sphere, where b is between a and capital R. A cross-section of the sphere is shown in figure 1. So we have this sphere that is centered at the origin, which has radius capital R, and it has a hole. The hole has a radius a, which is less than the distance between its center and the origin, which is b. Okay, the solid part of the sphere, so this solid part, that is filled part of the sphere, has a uniform volume charge density rho. Find the magnitude and direction of the electric field inside the hole and show that the electric field is uniform over the entire hole. Hint, use the principle of superposition and the result of part A. Now we have a hole here, so this part has been emptied. At position r is equal to b, it's basically, let's assume that this is on the x-axis, and this has the hole has radius a, and we have the full sphere having a uniform volume charge density rho and radius capital R. Okay, so for a uniformly charged solid sphere with radius r, we can find the electric field inside without considering the hole first. We can take a Gaussian sphere with radius r inside, and using the same principle in part A, the closed surface integral E dot dA, because the area vector that is pointing radially outward will be parallel to the electric field vector. So this is going to be parallel to the area vector here, which is in the radially outward direction. Okay, so if I show an area vector here, this is going to be radially outward direction, and the electric field only depends on r. I have the Gauss law, which is stating that the electric field magnitude is a constant on the surface, and the area is 4 pi r square for this Gaussian surface, and this must be equal to the charge enclosed q in divided by epsilon 0. And what is the charge enclosed by this Gaussian surface? It's the charge density rho multiplied with 4/3 pi r cube. So we have rho multiplied with 4/3 pi r cube and divided by epsilon 0. This must be equal to the net electric flux. And I can see that 4 pi r square will get rid of this 4 pi and make r cube r. So I will find that the electric field due to this uniformly charged solid sphere without a hole in it is rho r divided by 3 epsilon 0. It's in the radially outward direction, so r vector is r in r hat direction. So basically, this is my r hat direction, which is the radially outward direction. Now, the problem statement says use the superposition principle. Now we need to subtract the electric field due to the uniformly charged sphere with radius a centered at B. Okay, so centered at R is equal to B. So that's basically the scenario we have considered in part A of the problem. So we can find the electric field inside the hole. So instead of treating this part of the space as a uniformly charged solid sphere with charge density plus rho, we can consider it to be with charge density minus rho. It has negative charge, so that the total electric field will add up and give us the end result with the solid sphere and subtracted portion equivalently having a negative charge. All right, so we can consider the electric field inside the hole to be the superposition of the electric field for the uniformly charged solid sphere rho r divided by 3 epsilon 0. And now I have the negatively charged portion, which has electric field rho r minus b divided by 3 epsilon 0. And this part comes from part A. This is from part A with charge density minus rho. All right, so we're subtracting that part. And this gives us, for the electric field inside the hole, E hole, to be rho b divided by 3 epsilon 0. Okay, so we see that this answer is independent of r inside the hole, so the electric field is uniform and in the direction of r is equal to b. So that's basically when r is equal to b, so it's in the direction of this vector, and it's basically uniform. So it's found by subtracting the contribution from a solid sphere of radius a centered at b from the full uniformly charged sphere. Okay, so we have once again the relationship here. R minus b is basically this vector here, which is basically this r prime vector. Okay, so we go from the origin to this point. This is basically my r prime vector, and r prime vector is r vector minus vector B. So that's basically what we did here. R prime vector is R vector minus vector B. So that gives us the electric field inside the hole. R minus B is the R prime vector. All right, so let's look at part C. A very long solid insulating cylinder has radius capital R. So this is my cylinder with radius capital R. Bored along its entire length is a cylindrical hole with radius A. The axis of the hole is a distance b from the axis of the cylinder, where b is between A and capital R. This is figure 2. You can see that I have a solid cylinder with charge density rho, uniform charge density rho, but then it has cylindrical hole centered at B and the radius A. Okay? The axis of the hole is a distance b from the axis of the cylinder. The solid material of the cylinder has a uniform volume charge density rho. Find the magnitude and direction of the electric field inside the hole and show that the electric field is uniform over the entire hole. Now, first I consider a uniformly charged solid cylinder with radius capital R. So that's what I have here. So I take a Gaussian surface with radius R less than capital R, a cylindrical Gaussian surface, in order to calculate the electric field. And then I write Gauss law, closed surface integral E dot dA. Because the electric field vector will be pointing radially outward here, so it's going to be parallel to the area vector. So this would be the radially outward, for example, area vector here, which is going to be parallel to the electric field vector that will be pointing radially outward from the center of this axis. So I will see that electric field E multiplied with the area. What is the area here? It is 2 pi r, the circumference multiplied by the height of the cylinder L, is equal to the charge enclosed by this cylinder Q in divided by permittivity of free space. How much is the charge stored? It is the uniform charge density rho multiplied with the volume, which is pi r squared L, divided by epsilon 0 in order to complete Gauss law. So rho times pi r squared L. Pi r squared is this area multiplied by the height L, gives us the total volume of this Gaussian cylinder. All right, so we have cancellation of pi rl here. So pi rl disappears from this side, and I'm left with an electric field E. I find for r less than capital R to be rho r divided by 2 epsilon 0. All right, so what is this vector R? R is R in r hat direction, so this is my r hat direction. So that's radially outward. Okay, so now similar to part A, if this is centered at B, then I would find the electric field for r less than capital R to be rho r minus B divided by 2 epsilon 0. Now you can see that if B is equal to 0, then this is centered at the origin, so I recover this case. It would be rho r over 2 epsilon 0. If it is centered at r is equal to B, then this is the right answer that I have discovered in part A also. So this gives me so that I will have the electric field inside the hole to be equal to the full cylinder has a contribution rho r divided by 2 epsilon 0 permittivity of free space. then I have the hole. So if it's a hole, it should be considered as negative charge minus rho r minus b divided by 2 epsilon 0. And this gives me an answer for the electric field in the hole to be rho b divided by 2 epsilon 0. That's the permittivity of free space. So this answer is independent of R. So you can see that it's a uniform electric field inside this hole. And I note that in part B and part C, if B is equal to 0, then the electric field inside the hole is 0. So let's think about this. If you place this cylinder at the center, so that B is equal to 0, that coincides with the central axis of the full cylinder, then you would have 0 electric field inside. Why? Because the positive contribution and the negative contribution from this cylinder would cancel out, and you would have 0 electric field inside this hole, which is expected because if you take this cylinder here and then take a Gaussian cylinder with radius less than a, you would see that there is no charge inside, and that means we should have 0 electric field. The same is true for this spherical charge distribution. So electric field inside the hole is 0 due to cancellation of fields from the two solids with equal and opposite sign of charge densities. Okay, so to summarize, we have considered two related problems here. So first we started with the problem of having a uniformly charged sphere centered at not r is equal to 0 but r is equal to b. What is the electric field inside the sphere? So there we have used Gauss law. Now the center is at r is equal to r vector is equal to b vector. And if I go to any other r vector here, so that the radial position vector in reference to the center of the sphere is r prime, and r prime is r minus b, or r is equal to r prime plus b. So if it is r prime plus b, you would get this vector. This is r prime in r prime hat direction. So if I take a Gaussian spherical surface, and I note that the electric field and area vectors are parallel and electric field magnitude is only a function of r prime, so that it is a constant value on this surface. Writing Gauss law, E times 4 pi r prime square, charge enclosed by this surface divided by epsilon 0. The charge enclosed is the volume of this sphere, 4/3 pi r prime cube, multiplied by this uniform charge density rho. And that gives me the electric field for this r is equal to r prime to be rho r prime divided by 3 epsilon 0. Because of this relationship between the vectors, it is rho r vector minus b vector over 3 epsilon 0. Now if I consider in part B a full cylinder which is centered at r is equal to 0, so that means b is equal to 0. If b is equal to 0, then I have rho r over 3 epsilon 0 as the answer. But now I have a hole inside this spherical region for which the center is r is equal to b. So that means instead of considering this electric field, I should use a minus rho in order to subtract the contribution from this whole spherical hole here, which would normally have a plus rho r minus b over 3 epsilon 0. So if I subtract that from the full contribution, rho r over 3 epsilon 0 minus rho r minus b over 3 epsilon 0, I find the electric field in the hole, rho b over 3 epsilon 0, independent of r, it is uniform. The related problem is a cylinder, a uniform cylinder has an electric field inside rho r over 2 epsilon 0, which is easily found considering a Gaussian cylinder inside this cylinder with radius r less than capital R. So here I have r less than capital R. And this gives me E times 2 pi RL, because electric field and area vector are parallel. It's only in the radially outward direction, originating from the reference as the central axis of the cylinder. E times 2 pi RL is rho times the volume of the cylinder, pi r square multiplied with L over epsilon 0 gives me rho r over 2 epsilon 0 for the electric field inside. If it is centered at r is equal to B, instead of rho r over 3 epsilon 0, I had rho r minus b over 3 epsilon 0. Here I have rho r minus b over 2 epsilon 0 for the cylinder case. Now, if it has a hole centered at B, radius A, it's rho r over 2 epsilon 0 minus rho r minus b over 2 epsilon 0. I find the electric field inside is uniform again. It's rho b over 2 epsilon 0. If the B is 0, then I would find that the electric field inside the hole should be 0 for both cases. So this tells me that the positive and negative charge contributions from the two solids with equal and opposite signs are actually cancelling out.